Hello everyone, welcome to my talk, In-Network Memory Access Ordering for Heterogeneous Multicore Systems. My name is Jamie Ying. I'm an assistant professor with Lehigh University. Writing parallel programs has never been easy, and it can be more challenging in the future. A future computer system might have CPUs, GPUs, FPGAs, and different types of accelerators integrated together. And the memory hierarchy itself can be heterogeneous. For example, there could be processing memory, non-volatile memory, flash storage, and die-stacked DRAMs like HBMs. These components can be integrated together inside the same package and connect with each other through an on-chip or in-package interconnection network. And you can probably imagine writing parallel programs for such a heterogeneous system can be very challenging. One of the challenges that programmers face is a memory consistency issue. Let's say we have a system with 4 cores and 2 memories connecting with each other through an interconnection network, and core 0 executes 2 instructions. First of all, write to X and then write to Y. And core 3 executes 2 instructions. First, read from Y and then read from X. Let's also assume X is stored in memory 1 and Y is stored in memory 0. And the expected program order is indicated by this arrow. So from core 3's perspective, the value of X and Y might have 4 possible combinations, while the first 3 results are kind of intuitive. But when it comes to the last results where X equals to 0 and Y equals to 1, you may want to ask, how did that happen? That means writing of Y happens before the writing of X, which apparently violates the program order of core 0 execution. But in real life, it could happen even if core 0 executes these 2 instructions in order and issues these 2 requests in order. Let's say core 0 is closer to memory 0. So request 1, which is write to Y, might arrive earlier and then modify Y's value to 1. And then request 0 from core 3 arrives and read the value of Y. Now core 3 sees Y equals to 1. And then request 1 from core 3, which is read of X, reads the value of X, and core 3 sees X equals to 0. And lastly, core 0 modifies the value of X. Now X becomes 1. This is how this last set of results happens in real life. And depending on the underlying memory consistency model of a system, this could be a valid result. But I guess to most people, this is not intuitive. And when it comes to debugging a multi-threaded program, it can be really difficult. Existing solutions include memory fence instructions or memory barriers. So with a memory barrier, operations issued prior to the barrier are guaranteed to be performed before the operations issued after the barrier. But this adds a lot of burden to programmers because it is entirely up to the programmers to decide where to add or where not to add the barriers. And there can also be endpoint ordering with hardware support. For example, total store ordering uses a store buffer to ensure that store instructions are executed in order. But endpoint ordering limits memory level parallelism. So the limitations of existing solutions motivate our work. Can we do something inside the interconnection network to maintain global memory access ordering so that we don't need to rely on programmers to add memory fence instructions, and also we can maximize memory level parallelism by removing endpoint ordering hardware restrictions. Here is an outline of today's talk. I'll briefly talk about our architecture design at a high level, and then go into details, including hybrid switching network, token ring network, and network interface design. And then I'll present our evaluation results and conclude the talk. Now, first of all, an overview of the architecture design. In order to maintain memory ordering inside the network, we need to make sure that two things are done correctly. First, point-to-point ordering, in which requests sent from the same source to the same destination arrive in order. To achieve that, we use a circuit switching network. So we set up a circuit switch path from a source to a destination, and critical requests will be using the circuit switch connection. And secondly, we want to make sure that global ordering is maintained. And to achieve that, we proposed a lightweight ring network to ensure that requests sent from the same source to different destinations are processed in order. So there will be a token sent in this token ring network. And by looking at this token, different memory points coordinate with each other to maintain global ordering. Now let me go into details. First of all, a hybrid switching network. A hybrid switching router supports both packet switching and circuit switching. And the diagram I'm showing here is a very classical pipelined packet switching router with multiple input ports, multiple output ports, and there could be buffers inside each input port. And to support circuit switching, we add circuit switching components, including a latch and a slot table to each input port. And the slot table keeps track of circuit switching reservation. Basically, is a given cycle assigned to circuit switching, and which output port is reserved. When a circuit switching packet message comes in, it will just take the circuit switching path without buffering. So here's an example of circuit switching path setup. Let's say router 0 wants to set up a path to router 3. And circuit switching messages will take this circuit switching path starting from cycle 0. So in router 1 and router 2, the slot tables needs to be configured appropriately, such that in cycle 2, router 1 is reserved for circuit switching, and similarly in cycle 4, router 2 is reserved for circuit switching. In order to avoid circuit switching path setup overhead, we will program the slot table at design time, and we've proposed a algorithm to do that in the paper. Now, coming to token ring network, which is used to maintain global ordering. The token ring network connects memory ordering points together. So a ordering point here could be a last level cache bank or a memory controller. Basically, that's the first level of memory hierarchy that is visible to all the cores. And the token router is really simple, just one input, one output, and the token can be consumed by the network interface and re-injected to the network. And with regard to token format, each critical request sent from a core is associated with a request ID here. And the network interface at an ordering point looks at this ID and determines whether or not to serve a request. And after serving the request, the network interface will set the corresponding flag in the token. So here we have 4 ordering points. Then we have 4 1-bit flags in the token. And each core will be assigned a field in the token because these cores operate independently, and the request ID is with respect to each individual core. And it's worth pointing out that there's at most 1 token in the network at a given time. So once the network interface consumes the token, there won't be any token in the network. and later on the network interface can re-inject the token to the network. Also, network interface needs to be modified to support in-network memory ordering. So we provide each core with an reorder array to store and reorder the critical requests. Also, there's a token buffer and token examination logic in the network interface. Let's say there is a critical request coming from the main network, which needs to be ordered. And depending on which core sent the request will be stored in the corresponding reorder array. And then the network interface checks the token buffer. By looking at the request ID, it decides whether or not to serve a certain request from a certain core. And after serving the request, the network interface modifies the token buffer. And let's say now there's a token coming in from the token network, and the token examine logic will analyze the token, and the network interface will do two things. One, update the token buffer by referring to the token, and then it will update the token by referring to the token buffer. And after modifying the token, the network interface re-injects the token to the token network. Let me show you a concrete example. Let's say we have 4 network interfaces, 1 through 3. And inside each interface, the reorder array is keeping track of the critical results requests from a given core. Let's say the core issued 3 requests. The first request is a broadcast. The second request is a unicast only to network interface 1. And the third request is a multicast. Now, token buffer and token are initiated as following. So all the network interface will look at request number 1, and the token also says that everyone will start serving request number 1, and all the flag bits are unset. Now, when the token is circulating on the token read network, the network interface will start serving request number 1. And once all the network interfaces finish serving request number 1, one of the network interface will update the token and then set the request ID to 2. So from now on, everyone starts serving request number 2. Notice that in network interface 2 and 3, there is no request number 2, but instead there is request number 3. Remember, point-to-point ordering is guaranteed by circuit switching. So as long as a network interface sees a 3, it knows that there will not be a 2 anymore. Therefore, NI2 and NI3 set the corresponding bits. And NI1 has a request 2, so after serving, it will set the bit as well. When it comes to NI0, it does not have a 2 or a 3, but NI0 sees all the other NIs have begun serving request number 2, so it starts to time out. After a certain number of cycles, NI0 still hasn't received any 2, so it will just set the bit to 1 and then update the token. So now everyone starts serving request number 3. For evaluation, we use Gem 5 GPUs and Garnet, and we evaluated the 16-node system and the 36-node system. And for comparison, we compared our design against packet switching NLC with minimum adaptive routing. So this is an unordered network. It might not guarantee the correct program execution. And also we'll compare against endpoint ordering, which is total store ordering using store buffer. And we use linear benchmark suite. So the figures here show the overall execution time comparison against three types of networks: unordered, core, and ordered, and our proposed network ordering network design. And overall, our proposed design guarantees the correct program execution and only impact the performance insignificantly. There are other results in the paper, including network latency, resource utilization, error and power overhead. Please refer to the paper for more detail if you're interested. In conclusion, we proposed a in-network memory ordering mechanism to ensure global memory access ordering, and that design exploits memory level parallelisms, and we think it is a very important step toward programmer-friendly heterogeneous programming environment for future heterogeneous systems. This is the end of my talk, and thank you.